All right. I like that term. Come up with that all on your own, or is that the fentanyl or whatever?
Yeah, I think that's
They give you the fentanyl in the hospital.
Oh, okay.
You know, they give you other stuff for at home.
You're not just like covered in fentanyl patches?
No,
Okay.
no, it would be amazing. It would be. I could show you a picture later when I got stuck in the shopping cart in the store.
All right.
It's great.
You're doing great. I heard about your food now.
Right. I'm telling you, I'm like crying. I'm like, I gotta make it to this semester.
You'll be okay.
All right. We got a couple more reactions to look at in Chapter 5, and then before we move to Chapter 7 next week. We may get there a little bit today, we'll see. But this part is called reduction of alkenes. And in organic chemistry, we use the terms oxidation and reduction a little bit differently, but we actually mean the same thing. So in your previous class, you probably talked about oxidation and reduction. Oxidation is you lose electrons, reduction is you gain electrons. And that's great when you're talking about ions and things going plus and minus and whatever, but our molecules are mostly neutral. And when we talk about reduction and oxidation, we can actually have an easier way of figuring that out. So when we say reduction in organic chemistry, one way that we can think about this is adding hydrogen to carbon. So specifically we're talking about carbon, but it works for other things too. And then we're actually going to use the term oxidation the way it was sort of originally designed. Remove H or add O. So when we add oxygen to stuff, we call that oxidation, as you would expect, which we didn't really do back in general chemistry. And if you actually want to work out the numbers, it still works out. So let's say we have methane, CH4, and if you remember calculating those oxidation states, H here, and if you don't worry about it, we're not going to do it. But in this case, H, the oxidation state of H is +1, and that means the oxidation state of C is -4, because it's overall neutral. And then if you compare that to something like CO2, if you use those rules, you find that the oxidation state of O is -2, and the oxidation state of C is +4. Again, if you don't remember all those rules from Gen Chem, don't worry about it. We're not going to use them. I'm just trying to demonstrate it. So what we can see here is in this reaction, if this were a reaction where methane became carbon dioxide, like in a combustion reaction, carbon goes from -4 to +4, which is oxidation by the definition of losing electrons. But it's also oxidation by this definition of removing hydrogen or adding oxygen. So CH4, we got rid of hydrogen, we added oxygen, and that makes it oxidized. Now with our alkenes that we're talking about now, we can take an alkene like ethylene, just a simple one, and we can reduce it by adding hydrogen to ethane. So we went from the alkene to the alkane. We added hydrogen, and that's considered reduction. If you go through and calculate the oxidation states of the carbons, you'll find that they do change in the way that we would expect with reduction. They get more negative. They add electrons, but we're not usually thinking about those oxidation states. So it's easier to just say we added hydrogen. That's reduction. Now this doesn't happen on its own. Hydrogen isn't quite reactive enough, and the alkenes aren't quite reactive enough to do this together. So we need a catalyst. And the catalyst, there's various catalysts that we can use for this. They tend to be in, sorry, let's stop going for a second. There we go. They tend to be in the what is that? The eighth row of the transition metals, eighth column of the transition metals. So nickel, palladium, and platinum are often used for this. The most common is probably palladium because it has a good compromise of not being too expensive, but still working pretty well. Nickel is used for some reductions as well. Sometimes you'll also see this written as palladium on carbon, like PD/C is when little particles of palladium are deposited on carbon. It's just a way of processing it. The palladium is still the thing that's doing it. Other options, as I said, sometimes you'll see platinum or nickel. The type of catalyst, for our purposes, doesn't matter unless you're actually trying to do this to a specific molecule. It doesn't matter what catalyst you use. On paper, anyway, it doesn't matter what catalyst you use. It's the hydrogen thing that's important. So this is known as catalytic hydrogenation. And sometimes those words get a little confusing too, because we have to remember hydration refers to water, hydrogenation refers to adding hydrogen.
Where is this PDC going?
Just somewhere under the arrow or something like that. As we did with the hydroboration, we're not going to look specifically at the mechanism for this because it's a little hard to draw because you're dealing with a solid substrate. So this is a reaction where you don't dissolve everything in the solvent. You actually keep the palladium or whatever as a solid, and you react the solution with it. So it's the alkene actually comes down and kind of sticks to the solid, gets hydrogenated, and then comes out. Because hydrogen's a gas, you also have to do this at pretty high pressure. I think there's a picture of the thing in here, yeah. So on page 146, you can see a picture of a hydrogenation chamber. Basically, you put your reaction mixture in here, and this motor kind of pumps up the hydrogen pressure, and you allow it to react for however long you have to react it, and then let it go. So most organic synthesis labs have a similar type of a setup for when you need to hydrogenate stuff. In line structures, hydrogenation looks nice, yeah.
So I'm having that, like, it all kind of looks the same as the conjugate base
Yeah,
acid.
okay.
And then it also kind of looks like protonation.
Protonation, yes.
Yeah.
It does. So the difference here is we're adding two hydrogens. So you're adding H2, one hydrogen to each side of the double bond, instead of just one hydrogen, which leaves behind a carbocation or something similar. But yes, I mean, transferring of hydrogen, it looks like protonation. In this case, it's not. It's a little different. The difference is more obviously pronounced when we look at the line structures. So if we take something like cyclohexene and we do this reaction, we reduce the alkene to the alkane. So you can just kind of see it. It almost looks like the double bond just goes away. And in a sense it does. But we have to also remember in our heads that it's not just disappearing, we're adding hydrogen. That's what's making the double bond not be there anymore. Okay, while we're looking at this stuff, this is kind of how we would describe the mechanism rather than actually draw it with the curved arrows. But what's happening here is the alkene is coming down onto the surface of the metal, where the hydrogen is also adsorbed onto there. And then the hydrogens kind of get transferred to it from the surface of the metal, and then it pops off again. So you can see like step 1, step 2, step 3 kind of is in the mechanism.
Why does not anything happen to the metal when it moves to the right? Like, why does it?
Because the metal is really only used to stick the stuff to it. So the metal kind of activates both the hydrogen as well as the alkene and allows them to kind of stick and come in contact with each other.
The metal doesn't need its hydrogen, is what I'm saying?
Right. The hydrogen isn't actually reacted really with the metal. It's mostly sort of stuck on the surface of it. Yeah, basically, it's a catalyst. It's acting like an enzyme. Yep. Yeah, the metal isn't really changed in the course of the reaction, and it can be reused. These catalysts, again, because they're expensive, they can often be reused. One thing that we can see from this mechanism, so actually I will copy it into the notes for you. Because the alkene kind of comes down to stick on the metal and then transfers the hydrogens that are already stuck to the metal, this is also a syn addition, which means the hydrogens are going to the same side of the metal, or to the same side of the substrate of the molecule. So for example, if we were to hydrogenate a dimethyl cyclohexene like that, we don't get either of the optically active or chiral diastereomers. We only get the meso compound because the hydrogens both add to the same side. So that's the only diastereomer we get as a product. We would not get this one, or it's an enantiomer. Because the hydrogens both have to come in from the same side.
So we could have it flipped, like the hydrogens could be both on the out, and the carbons could be both on the in.
Sure. Yeah. Yeah, but that's describing the same structure. And as the book says, if we're really being careful here, most of these reactions, when we say they're selective, they're not perfectly selective. They're mostly selective. They're selective to a certain percentage. So this actually is, if you actually do this reaction, you get about 70 to 80% this, and you get about 30 to 15% this. So you're favoring the syn product. And that's true with all stereoselective and actually regioselective reactions as well. We say, oh, the bromine only goes to this carbon. But realistically, because of all the statistical stuff involved with all these molecules smashing into each other, you're actually making a mixture of products. You're just favoring one over the other. So you always have to purify stuff out later. All right. So another thing to note about this is that the hydrogenation is not generally regioselective, which means if you have, let's say, some molecule like this, and you hydrogenate it, you're actually going to generally reduce the entire thing. Oops, redraw that. So it's very difficult to say, I only want to reduce this one alkene. Generally, if you're going to do reduction on a compound, it's going to reduce all the alkenes. That's also true with alkynes. So it doesn't just reduce down to the alkene, it reduces all the way down to the alkane. One exception to this is benzene. We'll do a whole chapter about, one or two whole chapters about these compounds. But you've probably seen this before. A 6-carbon ring with alternating double bonds is called benzene. And it is exceptionally stable because of those double bonds and their position. And when we get to that chapter, we'll talk more about why that is. But this molecule looks like regular alkenes, but it's really not. It's especially stable. So if you hydrogenate something like this, you will actually leave the benzene alone. And you'll hydrogenate the other alkenes anywhere else in the molecule, but you'll leave the benzene alone. You can reduce benzene, but you need a stronger catalyst and a little bit different conditions. Yeah. What? I mean, no, like, statements like that in chemistry are usually, like say all, if we ever say all of this or none of this, it's usually not quite true. So yes, there's other molecules that are similar to benzene that would have special stability that would be difficult to reduce. For our purposes, I think it's okay that we just leave that for now. All right, and then finally the last part of the chapter deals with reactions of alkynes, triple bonds. Alkynes can actually, as you might expect, undergo most of the same reactions as the alkenes. They can undergo addition of water, hydrogenation we just looked at, bromination, reaction with HX, all that kind of stuff. We're not really going to deal with that so much in this class because it introduces some other complications too. But they mostly act like alkenes. We know from what we've looked at that they're nucleophiles like alkenes. They can go out and attack stuff just like alkenes. So we're going to focus on where alkynes are different, like what they do differently from alkenes in this last bit. Yeah, Lisa?
So we talked about reduction in hydrogen. I can't say it, but we know what we're talking about.
Yeah.
But the oxidation, I don't see, where did we talk about that?
We didn't see any oxidation reactions.
We didn't see it yet?
No. We'll see oxidation reactions in a couple chapters.
So later on?
Yeah.
Okay.
What? I mean, it will be when we get to chapter 8, but not this test. Yeah. So alkenes, one special thing that alkenes can do let's take butane, for instance, is that as you saw in the last quiz, they can be a little bit acidic. Now, they're not really acidic, but they're just acidic enough that they can actually be deprotonated and form relatively stable negatively charged ions called acetylide ion. And the compound we usually use for that is called sodium amide, which is a salt of sodium and NH2 minus. So NH2 minus is the conjugate base of ammonia, NH3. So you deprotonate ammonia, you get an NH2 minus. It's a pretty strong base. And it's actually strong enough to deprotonate a terminal alkyne. So you can grab the hydrogen off the end of the alkyne, do an acid-base reaction, and make a negatively charged carbon anion. And then the byproduct there is ammonia, which is a nice byproduct because it becomes a gas and it's easy to get rid of. Now, this is still a pretty reactive species. Generally has to be kept pretty cold. We call this an acetylide ion. When we deprotonate a triple bond. But it turns out that even though it's a good base, it's also a decent nucleophile. And it can do something that we're going to look at in the next chapter called nucleophilic substitution, where it can actually substitute for a terminal alkyl halide. So what we could do here is add, let's say, ethyl bromide or bromoethane, so 2 carbons with a bromine. And this acetylide can substitute for the bromine. So it can come down and attack that carbon, attach to that carbon, and kick off the bromine. And that actually adds 2 more carbons onto the molecule. So you can use this to build a carbon chain and add onto acetylene that way. So then the byproducts here, you'd still have some sodium, you'd have some bromide, and then that ammonia. You'll notice that when we write these reactions, it's a little bit different from how you looked at reactions before. We don't focus so much on balancing stuff. We really kind of focus on the main carbon-containing structure, and then just kind of stuff comes in and goes out. Sometimes we just kind of forget about it. And that's because experimentally, we do this reaction, we're going to do some sort of a workup step, an extraction, just like you did last week, which washes all this extra stuff out. So if you did, let's say we did this reaction in ether, the only thing left in the ether is the product, the alkyne product. All the other stuff, the ionic, the ammonia, all the polar stuff, it's washed into the water layer when you do your extraction in the subtunnel. You dump that out, and then you can isolate your product from the ether. So the reason that this is kind of useful, computer's freezing at me again, is that we can use this now to actually build up structures. And one of the things that we're going to be focusing on as we get all these reactions under our expertise is we can actually look at a molecule and say, I want to make that molecule, and then come up with a sequence of reactions that ultimately leads to that molecule. So let's try that in a little bit of a small scale right now. All right, so let's say we are starting with acetylene, and we want to come up with a sequence of steps after which we can form this molecule. So 2 hexyne. So we want to start with acetylene and make two hexyne. So we want to come up with a sequence of steps to do that. And the way that we usually do that is to kind of work backwards. So we want to start with the product and think, what kinds of things am I going to have to do to make this product? So we look at similarities and differences from the starting material. So one thing I notice here is we've got our triple bond still there. So we can probably assume that that's going to be our triple bond from here. And then what we're really saying here is we want to add 1 carbon on one side, and we want to add 3 carbons on the other side. So we're gonna think about what kinds of reactions would make this sort of a bond here, and then what kinds of reactions would make this sort of a bond here, and that's how we can put this whole thing together. So when we're planning this,
Wait, pause.
Yeah.
Pause. Can you repeat that again? So what I want to do is have 1 carbon on one side and 2 on the other. Is that what you said?
3 on the other. Do you see the different parts there? one side of the alkene or the alkyne has a methyl or one carbon, the other side has 3 carbons. So we want to add some reagents that are going to make this happen. Now we can do this in a sequence of steps based on the reaction that we just learned. We learned that you can deprotonate acetylide ion and add some sort of alkyl halide, like a bromide, to make that part attach. So again, working backwards, we might think, all right, if we want to get to there, if we want to do like one thing to get to there, let's just pick a side. It doesn't matter. We'll do the smaller side first.
Why is the first one C?
No, there's not a good answer for that. It's a common name. So that molecule is just called acetylene. It was from before the rules were made up. The actual systematic name would be ethyne. So if we're naming it using the rules, we would call it ethyne. But because it's just a common molecule that we use a lot, we have this other name for it, acetylene. Mm-hmm. Yeah. Sorry, I'll try to remember that. Okay, so we can think about going from the molecule I just drew to the product by adding that methyl group. And that's something we just learned how to do. We learned that in order to do that, we have to first deprotonate with sodium amide and then use some sort of an alkyl halide to add that alkyl group. The way that we write that is in subsequent steps. Remember on Monday we talked about using 1 and 2 to talk about steps in order. We actually have to do this in 2 separate steps. So we would say that this is, first we would use the sodium amide to deprotonate. And then second, we would use the alkyl halide to do that substitution. And that would add that 1 extra carbon onto the alkyne. So then we got to do the next part. But we're getting closer back to the beginning. In these types of ideas, I know that it seems more direct to start from the beginning and go toward the end, but it's actually easier to start at the end and go back to the beginning. A mechanism, you work from the beginning and go to the end, but in a synthesis or trying to plan out how you're going to build something, it's easier to start at the end and go back. It's like a maze. If you know where you need to end up, it's easier to work your way backwards. So from this one then, we need to add this other section, these other 3 carbons. So we can do the same thing starting from acetylene. We can deprotonate the acetylene. And then we can add a 3 carbon group to get that other side on there. So in each case, we're deprotonating the acetylene and then substituting with one of these alkyl groups.
Deprotonating and then you're substituting with what?
Whatever you need. So in this case, we want to put 3 carbons on, so we use a 3 carbon group with a bromine to do that substitution. And then in the last one, we deprotonate again, the other side, and add the 1 carbon onto the other side.
So if we need 3 carbons though for the other side,
Yeah.
wouldn't it have to be like C2H6 here?
C3, we need 3 carbons. So we've got, let's number them off like this.
Okay, so at the top there, when you wrote CH3 bromine, you don't necessarily mean that it has to be exactly that?
No, I do. That CH3 is becoming this right here,
Oh, okay.
the 1 carbon there. And then the other side has 3 carbons, so that's why we need 3 carbons to add here to put onto that side.
Can you put number 2 in an outline structure? I'm just like overwhelmed. I can't do it for myself right now.
Which one?
Number 2,
Right here?
zigzag VR. What is
Yeah.
zigzag again? I'm so sorry.
that help?
Yes.
Okay.
Why can't we say we can just deprotonate once? Because I thought you said deprotonating isn't choosy, it goes everywhere.
I said hydrogenation wasn't choosy.
Hydrogenation is not, deprotonation is.
Right. It's not choosy in that it can grab either side, but we're only going to do one deprotonation.
But it'll only pick one side, it won't pick both.
Right. And then the second time there's only one hydrogen left over on this side, and so that's why we get the other side there. Yeah. Or putting them on, really. Yeah. Yeah.
But then how do you know, like, which ones to use? Is it always going to be NaNH2?
Yeah, so you're always going to use NaNH2 to do the deprotonation, and then you're going to choose the alkyl thing depending on what you want to stick on there. So in this particular case, we wanted to make a product that had 3 carbons on one side and 1 on the other, so we chose a 3 carbon and a 1 carbon. We could have switched the order of those two, and we would have ended up with the same thing. All right. The other alkene or alkyne reaction that we're going to look at is the reduction to an alkene. So we mentioned before when we looked at reduction, we said if you try to reduce a triple bond hydrogen with palladium catalyst, you're just going to always go all the way down to the alkane. You add all the hydrogen you can, and you don't have any triple or double bonds anymore. But there is a way you can use a catalyst that is kind of less strong, and you can limit it because an alkyne, the triple bond, is more reactive than an alkene, the double bond. So you can use a catalyst that's less powerful, and you can actually force it to stop at the double bond. So if we take, let's say, butine. Come on, I'm going to do that. All right, here's butine. And we saw this before. If we add hydrogen with our typical palladium type catalyst, we're going to make butane. Right, we're going to do that full reduction. Add all the hydrogen that is possible. If we don't want to do that, we use what's sometimes called a poisoned catalyst. So a catalyst that's been stuff's been added to it to make it a little less powerful. And there's actually a few different ways to do this. The book only talks about one, so we'll just stick to that one. The one that the book talks about is named after the somebody who worked on it, and it's called Lindlar's catalyst. It's still a palladium catalyst, but it has some, I think, barium sulfate, some other stuff in there to make it a little bit less powerful.
How is it spelled? I'm sorry.
Sorry, it's Lindlar. And if we do the reaction with that catalyst, we can actually make the alkene. And it is, again, a syn addition, so it ends up being a cis product, a cis alkene. So the regular catalyst, we go from two butyne to butane. With the poisoned catalyst, you go from two butyne to cis 2 butene. All right, so let's summarize this chapter. One nice way to summarize it is a little graph of reactions like we did before. So let's look at our alkenes first. Let's take our classic methyl cyclohexene, and let's look at the various things that we can do to it. So, for instance, we can add HBr. We can add HCl. We can add Br2 or Cl2. We can add hydrogen. We can add water with an acid catalyst. We can add water through hydroboration oxidation. Sorry, make sure you're with me there. Okay, and is that it? So make sure I didn't forget anything. Yeah, that's about right. We can add chlorine. Okay, so see if you can draw all the products that you would get for those various processes. Or if not all of them, see how many you could draw right now. And then that tells you what you need to study to look at a little bit more to get the other ones.
I can't read one and two. Yeah, what's one and two?
It's the hydroboration oxidation from Monday. BH3THF and H2O2 NaOH. Oh yeah, it is pretty small up there. Let me see if I can make it bigger once the computer stops being angry. So as you're studying with this, I want to also mark which mechanisms you should be able to draw. So I'll put a little star by the ones that I would expect you to draw the mechanisms of. Ones that you should be able to draw the mechanism on. To be able to describe what are each of the individual steps in that reaction. how do the electrons actually move throughout that process. So I will try to fill some of these in here for you. Describing the stereochemistry as well. Actually, that one won't be a stereo center. Okay, so there's a good summary of what we've done, at least for the alkenes. So that's it. We're out of time. Let's head over to lab and get started over there.
Wait, can I take a picture?
Hold on.